Now that we know what momentum is, we can talk about one of the ways that we use it. And even though we're not going to look too much at practical application here, do understand that this is one of the most important ideas in science. Not necessarily just with momentum, but this idea of a law of conservation of insert whatever word you want here. So in this case, the law of conservation of momentum means that momentum is not created or destroyed. And if we're going to get really specific about it, we can say that under certain conditions, so there are places where this doesn't apply, but under certain conditions, the total momentum of objects does not change during a collision. That is to say, if we add up the momentum of all the objects before a collision and after the collision, the total amount of momentum is the same. So momentum is transferred from one object to another, in a manner of speaking, and it's not lost. Now, let's talk about the conditions where this holds true, because it's only true in some certain circumstances. So it's true as long as there are no net, that is, no total external forces. Now, what we mean by an external force is this, is that the first thing we do when we're evaluating a system for momentum is to look at what we call the system. You've heard me refer to it sort of unthinkingly there. So in this case, our system, imagine we have these two balls rolling along the ground at each other. And our system is the things that we're focused on, the things that we're going to look at and evaluate the momentum of. And so in this case, we're evaluating the momentum of ball 1 and ball 2 total. As long as all the forces come from ball 1 or 2 and act on ball 1 or 2, as long as there are no forces from anything else, the law of conservation of momentum will be true. If, however, we use ball 1 and 2 as the system, and there's friction as they roll across the ground, that friction from the ground, that's an external force. The ground is not part of our system, so it's applying a force to our system from outside of it. So in this case, momentum would not be conserved. However, if we adjust our system to include the ground, that is, we're going to consider the momentum of ball 1, the momentum of ball 2, and the momentum of the ground, specifically all the little pieces or atoms of the ground that we're encountering, then friction from the ground would be an internal force, and momentum is conserved. Whatever momentum these balls lose because of friction is momentum that the particles of the ground are going to pick up. So as long as you define anything that's applying a force as within your system, then conservation of momentum will hold. It will be true. All right. Now we're going to look at some collisions and find out that there are actually two types. The first type we're going to look at is called an elastic collision. So that's a collision where there's no permanent change in shape or any transfer of heat. So in this case, kinetic energy, that is how much energy due to motion the objects have, and momentum are both conserved. So the momentum before and after the collision will be the same, and the kinetic energy before and after the collision will be the same. If you're not real keen on what kinetic energy is, don't worry about it. Just for now, it's a number that we'll be looking at. So we have the simulator that we can look at. And what you see here is ball 1, which has a mass of 1, and it doesn't say units on here. Let's assume kilograms. And I'm giving it a speed of 0.5, and this over here, P, remember, is momentum. So momentum is mass times velocity, so the momentum of this is 0.5. Ball 2 has a mass of 2, and I've given it a speed of negative 0.5. So more specifically, I should say this is velocity. That negative sign just means that they're going to be moving in opposite directions. Positive is this direction to the right, negative means to the left. In fact, I can put up some vectors here to show you. Those are the vectors representing the velocity of each one of these. So they're going to be moving towards each other, which means they will collide. Oh, excuse me, those are momentum vectors. I was wondering why they weren't the same size. So those are the velocity vectors for that. Now, if I hit play on the simulator, these two things are going to collide, and I've set this up to be a perfectly elastic collision. Now, I said an elastic collision is one where kinetic energy and momentum are conserved. There's an easier way to think about this. An elastic collision is just when they perfectly bounce off each other. They don't change shape or anything. It's almost like if you think two billiard balls colliding. You're playing a game of pool, you shoot the cue ball into another one, let's say the 8 ball, and they bounce off of each other almost perfectly without changing shape. We're saying that this collision is going to be perfectly like that. And we have a nice tool down here in the corner that shows the momentum. Momenta is just the plural of momentum. So it shows the momentum of each ball and the total. So this red arrow labeled TOT for total shows us the total amount of momentum. And what we'll see is that as I hit play and I let these collide, notice that that total momentum doesn't change, even though that the momentum of each one of those will be different. So there's the collision. Notice that amount of total momentum didn't change, but now some of the momentum that used to be with ball 2 has transferred to ball 1. So this is an elastic collision. Again, total momentum was conserved, and if we rewind and take a look, notice our kinetic energy at the start of this was 0.38 joules, and after the collision, 0.38 joules. So we can see kinetic energy was conserved, momentum was conserved in this collision. Now, interestingly enough, the way this calculates momentum, this red border is not part of the system. So any force applied to the ball from this red border is going to be an external force and will change the momentum. So if I let this play until they hit there, till they hit that red border, you'll notice that the total momentum does change at that point, showing us that this red line that they can bounce off of is not part of the system. All right, now we're going to go back and take another look at not an elastic collision, but an inelastic collision. So this is a collision where there is a permanent change in shape or a transfer of heat. Momentum is conserved, kinetic energy is not. So in this case, the kinetic energy will change, but momentum is still conserved. Now, we've got two confusing ideas, and I'll be honest, for a long time, especially when I was a young student first looking at these two confused the heck out of me because nobody very clearly explained to me what the difference between these two were. They used words like this, and I nodded and I smiled and had no idea what was going on. An elastic collision is where they bounce off of each other perfectly. If it's inelastic, they kind of stick a little bit, or they bend a little bit. So if it's a perfectly elastic collision, they'll bounce off each other without ever changing shape. If it's a perfectly inelastic collision, they basically stick together. So imagine taking two wads of putty and throwing them at each other, the way they would just stick together and move as one object. In an inelastic collision, things will change shape, they'll deform, and if it's perfectly inelastic, they'll stick together. So let's take a look at what that's like. I'm going to rewind this, but this time I'm going to set the elasticity to 0. So this is a perfectly inelastic collision. Notice again, if I give you some velocity vectors, they're moving right at each other. Also notice this interesting fact, is that one of the momenta is actually listed as negative. That's because this is a velocity, and so momentum will have this vector quality to it. So we list objects that are moving in different directions. One direction has a positive momentum, one direction is a negative momentum, which means if they have the same momentum and they're going in opposite directions, it cancels out and the total momentum is actually 0. So that was kind of an aside thing, but worth hearing. All right, notice in this case our kinetic energy, 0.38 joules, and our total momentum. Let's first allow these things to collide, and let's watch what happens to the total momentum. So they collide, and our total momentum stays the same. Again, we look at this and watch, and our total momentum does not change. Notice what the particles do, or these balls rather, is that when they hit, they stick together and move off as one object. So I can really combine their mass if I want to and think of them as one thing. All right, now let's look at the kinetic energy. 0.38 joules. After they collide, 0.4 joules. So we can see that kinetic energy is lost in this collision, meaning it is an inelastic collision.